Welcome! This resource aims to help you interpret basic radar imagery as a step in assessing the level of threat for a particular neighborhood location. This short presentation will focus on why radar data can be useful for assessing local area threat, how radar works and how we get the data, what to look for in radar imagery to confirm an imminent threat, and useful online sources of real-time radar data. Now, a neighborhood storm watch can operate based solely on warning issuances, alerting neighbors when a warning is issued that includes the local area. However, severe weather tends to occur only over a small portion of the warning area. Here's an example, with a storm tracking across the northern half of a warning area shown in red. So the main threat area is shown in this white polygon. Areas in the southern part of the warning area are not in imminent danger, with the storm passing to their north. Here's another example with a northward moving storm. The threat area with this storm on its track is shown in white, so areas in the western and eastern portions of this warning area are also not in imminent threat. And finally, another example where the threat area is tracking right along the middle portion of the warning area, shown in white here. So areas in the northern and southern portions of the warning polygon are also not in imminent danger. By combining warning displays with radar data, one can downscale the threat to a smaller area, reducing unnecessary alerts in areas that will not be affected by the warned storm. Doppler radar consists of a transmitter that rotates within the radar dome. The transmitter transmits a pulse of energy as it rotates around, and then listens for any of that energy to be scattered back to the radar by distant targets. That small amount of energy is what leads to our radar products. The two key types of products are reflectivity and velocity. Reflectivity relates to the strength of the energy returned to the radar by the target. Greater energy back relates to greater reflectivity, and that greater energy tends to come from larger or more numerous targets. On this image, larger or more numerous targets are reflected by the warm colors, while fewer or smaller targets are shown by the cool colors. So this image shows light rain in green, moderate rain in yellow, heavy rain in orange and red, with very heavy rain or hail in dark red, magenta, or purple colors. Velocity data show the component of motion of the targets toward or away from the radar. It is more challenging to interpret because it only shows a component of total motion, that is, the component either toward or away from the radar site. Flow that's perpendicular to the radar beam cannot be detected. Thus, it's easy to misinterpret what velocity data are showing. As a result, this presentation will only focus on reflectivity data. The velocity data will not be covered due to interpretation difficulty. Another type of product is the radar rainfall estimates product that I will briefly touch upon. So, what on reflectivity data should you look for when it comes to assessing imminent threat of a hazard? Here are the key clues. High reflectivity cores in dark red, maroon, purple, or white colors, which can indicate hail, as well as damaging wind potential. These hazards also occur within the strongest part of the storm, which is typically reflected where you have tight gradients of reflectivity. That is, where the colors change rapidly from green to orange or red over a very small area. This typically occurs in the southern portion of individual storms or along the leading edge of storm lines, with a weaker gradient, thus a broader change of color over space, occurring on the north side of storms or back side of lines. On the right image, note how the colors rapidly go from blue to red on the southern side of the storms, and much slower to change on the northern side. This indicates greater intensity and potential for severe weather, including hail and tornadoes, on the southern part of the storm compared to the northern part. An important thing to point out is that online, you generally access only the lowest radar slice, so you only see the lowest part of the storm. However, a thunderstorm is a three-dimensional object, and the upper part of the storm could tilt away from the lower part. Thus, it's important to give a little room for error when looking just at the lowest slice. In this example, on the upper left image, the storm appears to be passing to the north of point X as it moves towards the east. But as you look higher up in the storm, as you go clockwise around these images, note that the upper portion of the storm is partially tilted over point X. Thus, there's potential for hail or winds to occur at point X, even though it might appear on the lowest slice like the storm is passing to the north. Now, there is a reflectivity product called composite reflectivity that can show elevated cores of the storm that you can't see on the lowest slice.
Here's an example, and you see on the base reflectivity product, the lowest slice, there's not a lot of reflectivity within the center of the oval. But if you look down at the composite reflectivity, it is showing high reflectivity values that are further aloft in the storm and that cover the center part of the oval. And so the composite reflectivity might be a useful product for tracking big cores that could be approaching your neighborhood. Some of the radar apps may have composite reflectivity. I know the government site, radar.weather.gov, does have it in its menu.
For thunderstorm lines, curvature that develops over time within the line means something is going on, usually related to strong winds. So a bowing of the line, or curvature developing within it, can be a damaging wind signature, especially when you have a tight leading reflectivity gradient, that is a sharp change from blue to orange or red along the leading edge of the line. If you see enhanced curvature or kinks along the line, as shown on this image, that can be a clue for tornadoes, as well as damaging winds along that portion of the line. Often, tornadoes or strong winds from isolated storms are associated with a kidney bean or fishhook shape in the southern or western part of the storm, as shown here. Once again, note the much tighter reflectivity gradient, going from light green to red over the more southern part of the storm, the more severe part of the storm, compared to the northern part, where severe weather is not occurring. Fast-moving storms or fast-moving lines are often associated with damaging winds. You can get a sense of storm motion from the warning product itself. Here's an example for a line of storms moving east at 55 miles per hour. Finally, for the flood threat, simply look for areas where orange or red shades sit over or continuously track over, thus indicating a lengthy period of heavy rain for that location. So this example of a potentially tornadic storm could also be a flood producer if it moves very slowly. Okay, give this example a try. Your neighborhood is in Phillipsburg, and we have a northeastward moving storm. Do you see anything that suggests a potential weather hazard? You should note a high reflectivity core that suggests hail or wind that's likely to occur, and that's why the warning is in effect. Given what you see here, do you think your neighbors need to take cover from this storm? Unless the size of the storm grows, the northeastward motion will take the storm north of your neighborhood. So despite being within a warning itself, this is an example where close monitoring is necessary, but notification to take immediate action may not be needed. Now, what if, in this example, the storm was moving due eastward? That would take the southern part of the storm, which is likely the severe part, to right over the neighborhood. So in this case, yes, neighbors should be notified to take cover. Let's try another example, this time for a line of severe storms. The potential for damaging winds is high due to the fast motion of the line and the tight leading reflectivity gradient going quickly from green to red over a very short distance. Let's say your neighborhood is in the town of Purdy. On this reflectivity image are outlines of expected line location in 10, 20, and 30 minutes respectively, given that the line is moving quickly eastward at 50 miles per hour. Warnings are in effect, likely for the potential for 60 to 70 mile per hour wind gusts along the leading edge of this line, again where we have a tight reflectivity gradient, particularly for the southern portion of this line of storms. Should your neighbors be notified of the warning now in effect and the line of storms heading their way? Hopefully you got the answer right in by saying yes. Purdy is directly in the path of this line of storms, particularly the more intense southern part of the line. So what should you communicate to them? Which answer seems best? In this example, the correct answer is C. Purdy is not only directly in the path of the storms, but the storms are likely 10 minutes away or less. It's time to notify neighbors to take cover. It is very important to mention that online radar imagery is typically delayed 5 or 10 minutes behind real time due to the time it takes for the data to be processed, shipped to a central server, and then sent to the app displays. In this example, the storms are likely a bit closer to Purdy than this image suggests. So although the image looks like the storms are at least 10 minutes away from Purdy, in reality, arrival will likely be sooner. Now let's assume that your neighborhood is in Springfield, a few counties downstream from the line, but still within the warning area. Would you notify the neighbors in this case? The answer is yes. Definitely notify them that a warning is in effect and that the line of storms is approaching the neighborhood. But what would you indicate to them? Should they take immediate cover? Probably not yet, since the storms are still 20 to 30 minutes away, and the line could weaken before getting to Springfield. In this scenario, answer B is best, in which you closely monitor the line's progress, notifying neighbors to take cover when the line gets within 10 minutes of Springfield. Again, be careful of the delay in the radar data you see. What looks like 20 to 30 minutes away might only be 15 minutes away in real time. Some sources of radar data may provide rainfall estimates. This represents a rough estimate of rainfall that has occurred based on the reflectivity pattern. Where high reflectivity resides the longest, and thus heavy rain has occurred for the longest period of time, the rainfall estimates display will show the greatest amounts. Here we see an example where a few areas of excessive rainfall of 3 inches or greater are detected. Flood warnings are issued for these heavy rain areas. So in this scenario, assuming your neighborhood is in the town of Braceville, what might you communicate to your neighbors? With a flood warning issued for Braceville, now is the time to notify neighbors of the likelihood of flooding in the area, given the heavy rainfall that's occurred. There are a number of radar apps available, and they come with different features and at different costs. Costs usually range from free if they contain ads to $5 to $10 if they do not contain ads. Now, we're not going to recommend any particular app. These are just examples shown. But there are some points to keep in mind. First of all, that radar imagery from these apps and online can be delayed from real time by 5 or even 10 minutes. And this needs to be accounted for, especially if you're trying to time storm arrival. What do you need from a good radar source? Well, you need the ability to view radar data, to highlight your location, and to zoom in and out. The ability to run a time-lapse animation so you can interpret storm motion and future track. The ability to plot warning areas over the radar data. And again, you want a source that has data within 10 minutes of real time. There is a website that NOAA operates, radar.weather.gov, that also provides radar information, but again, it also can be delayed 5 to 10 minutes from real time. Here's a quick look at the radar.weather.gov website. That page provides radar data all across the country. You can click on Select View and see all the radars around the country and click on a particular location. You can then zoom in on that particular location. In this case, I selected Des Moines, Iowa, and it shows the reflectivity imagery for that radar site. You can again zoom in and out. The more you zoom in, the more detail you'll see in terms of where the counties are located and where specific cities are located. You also have a scale below to indicate what the colors mean, as well as a tool to be able to play an animation to assess storm motion. There's also a variety of products available. You have the reflectivity, there is velocity, although it's challenging to interpret. You also have precipitation accumulation as well, which are the radar rainfall estimates. Here I've zoomed in on the Des Moines area, and you can see again the towns that now appear around Des Moines that you can see relative to where the storms are. Unfortunately, unlike some of the apps, this site doesn't necessarily show you your precise location. So you would have to know where you are within a county highlighted or how close you are to a given town. I hope this video is helpful when it comes to basic radar data interpretation applied to assessing the existence and timing of potential weather threats to your neighborhood. Thanks for watching.